purpose of this lab is to observe induced electric fields using a solenoid, a bar magnet, and an oscilloscope. The oscilloscope is basically a voltmeter, so just like any other voltmeter, it measures a voltage difference. Here's one of its inputs. We don't have anything hooked up to that right now, so that's why it's measuring 0. There's an outer conductor, which is normally grounded, and then there's a central conductor, which is the other contacts, and so it's going to measure the central conductor's voltage minus the outer conductor's voltage. Now I've hooked up a banana plug to BNC converter to that input, which I'll use in a minute. The voltmeter measures a voltage that's time varying. So you can see that the trace is sweeping across the oscilloscope at a certain speed, and that's its real purpose, is to measure a graph of the voltage difference on the input as a function of time. If I hold it a little closer, you can see down on the bottom left it says channel 1, 1 volt. What that means is that each of those little 1 centimeter graph paper squares is 1 volt tall on the scale that I'm currently on. And then for the scale on the x-axis, you can see here that it says 1 second. That's why it's taking 1 second for the trace to move across 1 square. A voltmeter normally is not going to work properly if you don't have it hooked up to anything, and this one's no exception. So what you're seeing is some noise, and that noise is kind of varying irregularly when we wiggle the contacts on the banana to BNC connector. So that thing's acting kind of like an antenna, but not a very good antenna. So now I can demonstrate how I can change the scales here. There are controls for both the vertical and the horizontal scale. We were on 1 volt per division. I'm going to now turn this knob clockwise, and that's going to have the effect of zooming me in. So now I'm at 500 millivolts per division, 200 millivolts, 100 millivolts per division. So now that background noise signal just appears magnified. If I go ahead and hook up this banana plug cable to the inputs. So now I'm just taking this piece of wire and shorting directly across the 2 inputs, the oscilloscope. That's just a loop of wire there. Anytime you have a conductor, you expect it to have a constant potential throughout. So in this sort of circuit, we would expect there would be 0 voltage difference between the 2 inputs to the scope, and that's pretty much what we're seeing. So we're now using the voltmeter, the oscilloscope, the way it's intended to be used as a voltmeter, and it's doing its job and correctly measuring that there's 0 voltage difference. Now let's try that with this solenoid instead of that blue piece of wire. The solenoid still is basically just a piece of wire. It's a big long spool of wire with 3,400 turns in it. It's about 10 centimeters in diameter and about 10 centimeters wide. It has electrical connections at these banana plugs right here, and you can see the yellow wires right behind there. Those yellow wires wind onto the solenoid, and at one point in this lab it'll be important to figure out which way those go. So for instance, this one actually winds onto the coil this way, going around counterclockwise from your point of view from the camera. So here's the oscilloscope. And here's the solenoid. hook up one connector from the solenoid onto the input. Now the other one. And just as before, once I complete the circuit, the voltmeter starts acting like a good voltmeter. We see exactly what we expect, which is 0 voltage between the two ends of a piece of wire. It's not a perfect conductor. We've got thousands of turns worth of wire on here. In a skinny wire that long, the resistance is actually pretty significant. But even so, we're going to get 0 voltage because there's no source of voltage in the circuit, and the wire is a pretty good conductor. So the point of all this was to observe induced fields. Now, previously in this course, you've used those solenoids to create magnetic fields, like by hooking them up to a battery or a power supply. I want you to realize that there's nothing like that going on here. This solenoid is just hooked up to the oscilloscope, which is a meter, not a power supply. So it's not creating its own magnetic field. And just to make sure you can see that, I'll bring this magnetic compass in here. You can see that the red side of the compass is pointing toward the camera. If I then move it closer to the solenoid, nothing changes. There's no magnetic field coming from the solenoid. All I'm seeing here is the magnetic field from the earth or whatever magnetic building materials I have in my house. So the point of all of this was to see So the point of this lab was to observe induced electric fields. The voltmeter is basically an electric field meter. A voltage is one way of finding out about electric fields. If there's a voltage difference between two different places, that's an indication of how much work would be done by the electric field moving a charge from one point to another. And the way we have this hooked up right now, this solenoid is acting as a voltmeter that, or an electric field meter that would be able to measure electric fields that sort of swirl around in circles like this, because that's the kind of field that would be able to drive a current through that coil. So that would be an electric field that you could say was swirly, or it has a curl to it in terms of the curl operation from vector calculus. You could say that it's a non-conservative field. Electrostatic fields are never curly like that. They're always conservative. So as far as an electrostatics experiment, we expect to see exactly what we see here. We get no curl in the electric field. Now I've got my magnet, and I'm going to move the magnet suddenly toward the solenoid, and you can see it creates a big spike. Now at this point, I'm going to start the actual observations for the lab, and so in each case, I'm going to describe to you what I'm going to do. I want you to pause the video for a second, think about what you expect to happen, and make a prediction. Then I'll do it, write down what actually happened, and if you need to, pause again to think about why it happened that way if it wasn't what you predicted. And then in your write-up, you're going to describe all these observations and try to explain them. So in my earlier observation, I took the magnet and I put it right here and moved it suddenly toward the solenoid and got a positive spike. And now I want you to think about what will happen if I flip the magnet around. So just so we're clear on what's what here, I'm going to take a rubber band and wrap it around one end of the magnet. So now with the rubber band end toward the solenoid, I get a positive spike. Now I'm going to flip the magnet back around, And I want you to pause the video now, think about what you expect to happen, then continue playing the video and see if it's what you expected. So now the magnet's flipped around, the rubber band is on the left side, but I'm going to do the same motion straight toward the solenoid. So we see a negative pulse. There's a little bit of a positive backlash there, but the main thing is that big negative spike. Next, I want you to think about what will happen if I go back to my default setup with the rubber band side toward the solenoid, but do the motion more slowly. Pause and think about that for a second, make your prediction. This will be part B. The part we just did a minute ago was part A. So for part B, I'm now going to go ahead and move it more slowly toward the solenoid. So we get a spike, but it's a smaller spike. Next, we're going to do part C. In part C, I'm going to start the magnet near the solenoid and then move it away from the solenoid. And notice now how I'm inserting the magnet slowly into the setup. As you've seen, that causes there to be almost no induced fields. That makes it easier for you to see what's going on. So I've got the magnet close to the solenoid. I'm going to snatch it away in the direction away from the solenoid. Pause the video, make your prediction, and then we'll see if your prediction was right. So we got a negative spike. Next observation, which will be part D, is I'm just going to leave it at rest inside the solenoid. So I'm going to turn the solenoid around to you like this, prop it up so you can see it a little bit better. And then I'm just going to stick the magnet inside. The magnet's field is very intense when you get up close to the magnet. So we'll be putting a strong magnetic field inside the solenoid. Pause the video, make a prediction. Okay, now I'm going to go ahead and put the magnet in there. So there was that negative spike while I was putting it in, but now we're doing the actual observation for part D, which is just what happened. The magnet is sitting there inside the solenoid, and we see that there's zero signal. So just to summarize the parts we've done so far, those were the 4 things we did so far. Next we're going to do part E. Part E is going to be sort of a combo of A and C. In other words, I'm going to flip the magnet around so that the rubber band side is on the left, and I'm also going to reverse the motion so that I'm chopping the magnet away from the solenoid. Getting ready for that observation. So pause the video, make your prediction. Okay, now I'll do it. And you can see that I got a positive pulse there. Next I'm going to do part F. For part F, I'm going to keep the magnet stationary and move the solenoid. So to get the magnet in a good position relative to the solenoid, I want it kind of on axis of the solenoid. So I was looking around for something to use for that. I happen to have this around. So I'm going to put the magnet inside the martini glass. And it's pretty hard to move the solenoid as fast as I can move the magnet. But I'm going to do the best I can. I'm just going to shake it back and forth, trying to move it as rapidly as possible. So you'll see the polarity oscillating. It's like an AC signal. So pause the video, think about what you expect, and then we'll do it. So I think you can see there was a signal there. run stop button. It's a little bit small and hard to see, so the amplitude is not that big. I can move the oscilloscope close up to the camera. So you can see that we did get an effect. And so it oscillates as I move the solenoid back and forth. I could have demonstrated a pulse just by trying to move the solenoid one way or the other. That's a little bit harder to do physically. Let me give it a try and see if I can do it. So there's the magnet back in place. And I'm going to unpause the oscilloscope so it starts making a trace again, and see what happens if I jerk the solenoid away from the magnet. So there I got a pretty strong negative pulse. So that's a good example to think about. So we have a definite polarity on that. So I had the rubber band side of the magnet on your right, and I pulled the solenoid away suddenly. So that was part F. So recapitulating what we just did, part E was a combination of two things: flipping the magnet so the rubber band side was on the left, and also reversing the direction of motion so the magnet chops away from the solenoid. And then part F was where I moved the solenoid. I'm going to do another quick demonstration here, which you don't need to write down observations about, but it's just kind of cool to see. So what I've done here is I've taken some Scotch tape and taped the magnet onto the end of a pencil. And now when I put the magnet near the mouth of the solenoid and spin it, I get an effect like this. So I get quite a strong effect, and to let you see that better, move it up close. So what's happening there is it's basically a sine wave, but the amplitude is so huge that it goes off scale, and the period of that sine wave is very short. The frequency is high. That's because when I spin the magnet like that, I can make the field change on a faster time scale than I can do when I'm just kind of waving the magnet around in the air. So if you think about that, by this point you should be able to understand both the reason for the bigger effect and compared to the other observations we've done, and also just the fact that the frequency is high, the period is short. Now for the final part of this lab, which is, in my experience, pretty challenging for a lot of students. We're going to look for a right-hand rule that explains the direction of the effects we've been seeing. So in order to do that, we have to look carefully at how the connections go onto the magnet and also onto the scope. So I think you can see in the video right now, there's a yellow wire there that connects from the banana plug connector down to the red wire. And then there's another yellow wire over here that connects from this banana plug cable down to the red magnet wire. So here's the black wire, and if we were to trace the circuit from the black wire to the banana plug connector, we would then go through the yellow wire, and it's important to note which direction that goes. It may be hard to see on there, but that yellow wire goes this way and then connects on to the magnet wire. So it goes this way. We would go around a bunch of times, and then finally we would emerge over here at this yellow wire, come out, go up to this banana plug connector and this red wire. So this could get pretty confusing, or you could forget. So to keep that from getting too confusing, I just made this little drawing, which I'm going to tape onto the front of the magnet. So what that drawing shows is the black banana plug cable going to the coil itself. I only drew one loop of the coil instead of all 3,400 loops. And then over here, that red line on the piece of paper indicates that coming off of there. The next thing we have to get straight is how this all works at the inputs to the oscilloscope. So I'll try to get this up close where you can see what I'm talking about. Remember, the red wire was in the red plug, the black wire is in the black plug, and I'm going to put them back that way again. So on this BNC connector here, it's got a red and a black connector, and also there's a little tab over here, and if I hold that up really close to the camera, you might be able to see that it says GND for ground. Totally illegible, but that little tab there says GND for ground. And what that means is that this connector connects onto the outer metal connector on the converter. That makes electrical contact with the outer electrical connector on the input, and that's the grounded side of that input. So then we've been seeing things like positive pulses, negative pulses on the scope, and we need to make sure we understand what that actually means in terms of an electric field. So here I'm just going to hold up a printout of a page out of my lab manual, and at the end of the video I'll also give the URL for this so you don't have to depend completely on the video. So that little picture there tells you what's going on when you see a positive pulse on the scope. So if there was a positive pulse on the scope, the pulse is telling you that inside itself current was flowing from its positive end through the body of the scope back out to the ground end, because that's what would happen if you hooked up a battery to the scope with a high voltage on that side and a low voltage on that side. But all it really measures is the direction of the current through itself. So if current was actually coming in the central connector through the scope, coming in the, yes, that's correct, coming in the central connector, going through the scope, and going back out through the ground, which is the external shell, it would then, to make a complete circuit, would have to go out this way, the way that little arrow shows, around this loop of wire that way, and back in that way. So if you see a positive pulse on the scope, this diagram is telling you how to interpret that in terms of electric fields. It tells you there's a swirly electric field going this direction from the ground tab side to the other side. And the final thing we need to observe carefully if we're going to get this right-hand rule right is the polarity of the magnet. So right here I've hung it from a second rubber band, so it's acting like a little magnetic compass. The camera is pointed south, and you're seeing the magnet orient itself so that the side that was not marked with a rubber band is toward you. So if I turn it sideways, you can see that the part that had the rubber band wrapped around it to mark it, that's the one that's pointing south right now. And I'm doing this inside. Often building materials have magnetic fields that are stronger than the magnetic field of the Earth itself, so I wanted to check. I went outside and I verified that the field inside my house really is in the same direction pretty much as the field outside on my front porch. So what that means is that this thing is lining itself up so that this end points north and the rubber band end points south. So there's some kind of arbitrary terminology about this, but the side that points north is called the north pole of the magnet. The side that points south is called the south pole. That has the weird implication that the Earth itself it is a magnet whose south pole is at the north pole, because the magnet's going to orient itself opposite to the Earth. I can also verify that this thing really is telling me the truth about what direction the field is pointing. I have it hanging from the rubber band because I didn't have a piece of string. So you could think, well, maybe it's just complying with the stiffness of the rubber band. So to check that, I'm going to turn my hand, and the magnet is still pointing pretty much the same way, even when I rotate the rubber band 180 degrees either way. So it really is responding to the Earth's field. And you may not be able to tell, it's also pointing down into the south a little bit. That's a real thing. That's because the Earth's magnetic field is not horizontal. So given that, we need to figure out the magnetic field pattern of this magnet. So here's a drawing of it. That black mark at the bottom of my drawing represents the rubber band that I used as a marker. And this is just one of these things that you kind of have to look up to get it straight. I don't have this memorized, but the convention is the magnetic field goes in the south pole and out the north pole. So here's the magnet. Here's the magnetic field pattern of the magnet itself, not the ambient reverse field, coming in the south end. And then magnetic fields don't have sources or sinks, they just form closed loops. So those magnetic fields are going to form magnetic field lines that look like this on that side, and like that on that side. And then when we use the magnet close to the solenoid, here's the solenoid up here, let's say. We're basically exposing the solenoid to the field that's sort of out here beyond the pole of the magnet on the magnet's axis. So in the example that I've drawn right here, the magnetic field is coming up out of the magnet. So the magnetic field made by the magnet as experienced by the solenoid would be in the direction shown by those two arrows in this particular example. So we did a whole bunch of different examples of positive and negative pulses when we did different directions of motion and had the magnet oriented different ways. Any one of those is sufficient to figure out the right-hand rule for induced magnetic fields. So I'm just going to recap one of those now that we've got all our stuff figured out in terms of polarity. So here's the solenoid. Red, black, same on the drawing, red, black. I'm going to turn the solenoid about 45 degrees to the side, like that. Then I'm going to just redo one of those earlier observations. So I've got the bar magnet over here. The rubber band end is toward the solenoid. We figured out that the rubber band end is the south end. That means that the magnetic field experienced by the solenoid right now is pointing this way toward the magnet, because that magnetic field of the magnet goes in the south pole of the magnet. Now I'm going to go ahead and chop toward the solenoid And actually there was a little bit of a backlash there, but that was, I believe, a positive pulse. I want to say that one more time to make sure I'm getting that right. So that was clearly a positive pulse with a little bit of a negative backlash there. Just to make sure I'm getting that right, because it's kind of critical, I played around with it a little bit and figured out that I was just going too fast, and therefore seeing too big a pulse. That small backlash was actually more prominent than it really should have been. I'm going to do it more slowly now. So now I think you can see clearly that the actual pulse is a positive pulse. So we're now going to have 4 hypotheses about how this relationship between the electric and magnetic fields works. This relationship is known as Lenz's law, and only one of these 4 hypotheses is right, and the data that I just showed you should allow you to figure out which one is right. So hypothesis number 1 says that when there's a magnetic field in a certain direction, there's an electric field that makes a curly pattern around it, and it's right-handed. So in terms of a right-hand rule, if my thumb is away from the camera, that would be the magnetic field according to hypothesis number 1, and then the electric field would curl in the clockwise direction as seen from the camera's point of view. Hypothesis number 2 is just like number 1, but it's a left-handed thing. So if hypothesis number 2 is right, then having my thumb away from the camera, that's the magnetic field, and the electric field would curl in the counterclockwise direction as seen from the camera's point of view. 3 and 4 are similar, but notice that delta there next to the B, so that's a different hypothesis. That delta is the change in the magnetic field. So if hypothesis 3 is right, then if the delta B vector is away from the camera, then the electric field goes in the clockwise direction as seen from the camera. So the delta B would be like the final magnetic field minus the initial magnetic field. And then 4 is the same idea but left-handed. So you should be able to look at your data and figure out which of these 4 is the correct one. And finally, I promised to give the URL of the lab manual. So there it is. It's lightandmatter.com. And the lab manual is under Physics 223, and this is Lab 7, Electromagnetism. This is basically the video demo version of the real-world lab that we normally do. The letters of the parts are different. Other than that, it's pretty much the same lab. There's 1 or 2 parts that are cut, and that's what causes the letters to be different.